Hi, there are many different types of problem which we can prove using proof by induction. Today I want to look at problems which involve divisibility. Let's first look at this function. Fn is 5 to the n minus 4n minus 1, where n is some positive whole number. Well, what happens if we put n equal to 1? If n is 1, we get 5 minus 4 minus 1, which is 0. N equals 2. 5 squared is 25, minus 2 times 4 is 8, minus 1, and that is 16. N equals 3. 5 cubed is 125. 4 times 3 is 12. 1. Subtract that, we get 112. 112 is actually 16 times 7. Let's look at n equals 4. 5 to the power of 4 is 625. Minus 4 times 4, minus 1. That is equal to 608. And that is 16 times 38. Well, if we take the first one and write that as 16 times 0, then each of these numbers, putting n equal to different values, each of them is a multiple of 16. Is this going to carry on forever or not? Can we prove that it carries on forever? That is what induction is all about. So let's look at this and see if we can. The task is to prove that this function is divisible by 16 for all positive integers n. So we start off with n equals 1. N equals 1, f1 is equal to 5 minus 4 minus 1, which is 0 times 16, and that tells us that f1 is divisible by 16. So the next part of our assumption, let's just make that look a little bit nicer. The next part of our assumption, or our proof by induction, is the assumption. Let's assume that fk, in other words, when n is k, that this is equal to 5k minus 4k minus 1 is divisible by 16. In other words, we're assuming that our statement above is true when n equals some number k. Well, let's say what that really means. That means that 16 times m is equal to fk for some value of m. We can write fk as 16 times a whole number. Well, the technique that we use for this is to look at fk plus 1 minus, I've left a little gap and I'll fill that one in later. Fk plus 1 would be 5 to the k plus 1 minus 4k plus 1. I've made a mess of that. Minus 1. So there's f of k plus 1 minus, and I have 5 to the k minus 4k minus 1. Now that sometimes works and sometimes doesn't in these cases. What I like to do is to choose a number here which will get rid of this power of 5. When I do that, I find that everything just drops out nicely for me. Well, that's 5 to the k plus 1. That's 5 times 5 to the k. If I put 5 there, I get 5 times 5 to the k. So if the number that I put in is 5, then I will eliminate my power of 5. So let's watch that happening. This is equal to 5 to the k plus 1 minus, let's expand those brackets, 4k minus 4 minus 1. Minus 5 times 5 to the k. Minus 5 times minus 4 is plus 20k. Minus 5 times minus 1 is plus 5. Let's see what happens here. 5 to the k plus 1 minus 5 to the k plus 1, they've gone. It's what we wanted. Minus 4 minus 1 is minus 5 plus 5. That disappears. And then we have minus 4k plus 20k is 16k. My 16 has appeared. And this, when I play this trick up here of eliminating the power of 5, then you are going to find the 16, the number that you want, appearing here. So now let's rewrite what we have. This tells us that fk plus 1 is equal to 16k plus 5fk. But fk, we wrote up here, fk is 16m. So 5 times fk is 5 times 16m. And now we've shown that fk plus 1 is a multiple of 16, or fk plus 1 is divisible by 16. So we have the same structure as we had with the other proofs by induction, that we've shown that the statement is true when n is 1. If the statement is true when n is k, it must always be true, or also be true, when n is k plus 1. It's true when n is 1, so it's true when we have f1 is divisible by 16, therefore f2 is divisible by 16. We've now got that f2 is divisible by 16, therefore f3 is divisible by 16, and so on in our proof by induction. Notice that I have written various parts in red, as I did in the earlier video. You must show that everything is true when n is 1, so I expect to see n is 1, and then a statement that the statement is true when n is 1, or f1 is divisible by 16. You must write down your assumption clearly, fully, and having done a logical argument, you can then conclude that the statement is true when n is k plus 1, that fk plus 1 is divisible by 16. I expect to see all of that in every proof. Then I expect to see you summarize it in the way that I've summarized it here. We've shown that f1 is divisible by 16, and that if fk is divisible by 16, then fk plus 1 will be divisible by 16. Therefore, fn, which is 5 to the n minus 4n minus 1, is divisible by 16 for all positive integers n by induction. You must write out the full proof. All the bits in red are essential. Let's look at another divisibility problem, similar to the previous one, but has certain differences. Let's first of all make sure that this is sensible. What happens if I put n equal to 1? 1 cubed minus 1 is 0, which I can think of as 0 times 6. So 6 divides. N equals 2 is 8 minus 2, which is 6. That's fine. N equals 3 is 27 minus 3, which is 24. 24 is 4 times 6. it looks as though it's going quite nicely. N equals 4. 4 cubed is 64, minus 4 is 60, which is divisible by 6. So this looks as though it's something which might well be true, but just proving it a few times or showing it a few times doesn't provide a proof. This is, again, ideal for proof by induction. We must show that it starts. Let's look at n equals 1. F of 1 is equal to 1 cubed minus 1, which is 0, which is 0 times 6. And so we can conclude that F1 is divisible by 6. Now we make the assumption. We assume that there is some number k, that Fk, which is k cubed minus k, is divisible by 6. Well, if Fk is divisible by 6, we can write it as 6m, where m is an integer. This time, we have no power to get rid of, and so we just look at f of k plus 1 minus f of k. F of k plus 1 is going to be k plus 1 cubed minus k plus 1, n cubed minus n, minus k cubed minus k. Well, I hope we're all good at working out a cube by now. Pascal's triangle, k cubed plus 3k squared plus 3k plus 1. Clear the brackets, minus k minus 1, minus k cubed minus minus gives us plus k. What happens here? Well, we've got rid of k cubed, which is nice. 3k squared doesn't do anything, it just stays there. 3k minus k plus k is just 3k, and plus 1 minus 1 disappears. That gives us 3k squared plus k, 3k. So it's 3 times k squared plus k, which I can also write as 3k times k plus 1. Well, my 6 hasn't yet appeared. I've got so far a multiple of 3. I need a 2. I've got k and I've got k plus 1. Well, k and k plus 1 are consecutive integers. So one of them must be even. Doesn't matter which one. If one of them is even, then the whole lot, k plus 1, must be even. So we could say that one is equal to 2 times, let's say, L, where L is an integer. Now we have that fk plus 1 minus fk is equal to 3 times, there's fk plus 1 minus fk, is 3 times k plus 1, that's 3 times 2l, which is 6l. There is my 6 that I would like to have. Now I can say that fk plus 1 is equal to 6l plus fk. Fk, if we look up at the top, is 6m. So fk I can write as 6m. And now we can see that fk plus 1 must be a multiple of 6. fk plus 1 is divisible by 6. Once again, I have written all the important pieces in red. We have n equals 1, therefore f1 is divisible by 6. Assume that our statement is true when n is k. Assume that fk is divisible by 6. Therefore, fk plus 1 is divisible by 6. And then the summary paragraph at the end. I do like to see all of that for every proof by induction. There are two more slight twists in examples on proof by induction, but these I will do in the next video.